Let's look at a 3-point test cross for mapping example. In class, I am going to hand out a sheet that has 2 examples. There are 2 links, one for the textbook tutorial and another YouTube tutorial showing you how to do this, and 2 more practice problems that don't have answers yet. I'll put up a key, but I wanted to walk through how you do this. So the 3-point test cross tells us the order of the genes and the distance between each pair, taking into account the double crossovers. If we don't take into account the double crossovers, we actually underestimate the distance between those genes. So it gives us a little bit more accurate distance than the 2-point test cross. Now both of these use 3 alleles or 3 genes with 2 alleles each, so don't get them totally confused. You need to take, if you are given the double crossovers, you need to take those into account. So let me go back one. There's a list here. The previous slide shows a summary of all the steps and how to do this. This is the same outline of steps that your book gives. If you watch some of the other videos, or if you Google or YouTube other videos, you might find slightly different steps, but they're all going to be the same steps. They might just be outlined a little bit differently. I am not going to ask you to calculate the interference and coefficient of coincidence. Just keep in mind what interference is, and that's in the previous video. So, I'm sorry, let me go back. When we are doing these crosses, mutant alleles are represented by the letters, a lowercase letter indicating that it is a mutant. Wild type are signified by a sign. Depending on the problem, they might also be written with the letter and a plus. So remember, the plus indicates the wild type. If you prefer one way to another, you can write them out however you would like, as long as you keep them consistent and keep the alleles as the letter. Okay, if you want to use plus or S plus for the wild type, that's fine. Just keep them consistent and don't mix things up. 3 alleles that are on a single chromosome are written together. A couple other notations: single SCO means single crossover, and DCO means double crossover. So I'm going to start by doing an example that is presented in a PDF that is posted on our chapter. It's called 3-point crosses. Now this is a PDF that someone has made from an example in another book, and it goes into a bit more detail. So I decided to do this one because you have that resource that allows you to see some more detail and a little bit more explanation. I'm going to stick to basically just doing the problem. All right, so our book says step 1 is to count the number of categories of phenotypes in the offspring. So here we have actually 8 different categories. We should have 8 different categories because that's the total number that you can get from the 2 alleles for each of 3 genes. Sorry, I got a little bit ahead of myself. 2 alleles for each of 3 genes produces 8 categories. Every once in a while, you'll see a problem where there's only 7. This indicates that double crossovers are very rare and you haven't actually seen any in the offspring. If that happens, you probably are going to have to determine which double crossover you're not seeing, which is a little bit hard. I'm not going to do that to you here. We're going to go through an example with all of the phenotypes. So the first thing after we count our number of categories of phenotypes is to identify the linkage arrangement. So this means that our book wants us to identify what are the parental phenotypes. So we identify the parentals because they are the most frequently occurring. So in this top parental, we have plus Z. So this phenotype is going to be wild type for V, wild type for W, and mutant for Z. So one parent has those phenotypes. The other parent is going to be mutant for V, mutant for W, and wild type for Z. So this is different than the discussion we had on the cross in lecture, because that one was all homozygous or all heterozygous, I believe. This one is a combo of both. So now that we know the parental phenotypes, we can move on to our next step. The next is to determine which gene is the middle by finding the least frequent pair of gametes. So let's label what all of these different pairs are. So we know the most common is the parental, and the least common are the double crossovers. They're not going to happen very often. So we could stop there. I'm just going to make a note that all of these other combinations are single crossover events, and we'll talk about those later. But right now we're worried about the double crossovers. So we are going to compare the double crossovers to the parental phenotypes to see which one is flipped. Now remember, in a double crossover event, your inner chromosomes are going to be the ones that are participating. So in this double crossover, if we have two crossovers here, what's going to happen is that we're going to get this chromosome cross over that one and that one. So we're going to end up with chromosome that is blue with orange in the middle. And that's how we get our double crossover. The other one is going to be the opposite. So we are looking for which alleles flip to the other chromosome and which alleles stay the same. So our parental set was plus Z and VW plus. Those are our parentals. Now our double crossovers are going to be VWZ and plus. So if we look at this, and I might actually write this the opposite way so we can see what has actually changed. You don't have to do this, but it might help you. You'll see why in a minute. If we write it the opposite way, we can see that V and W have stayed together. V and W have stayed together, but the Z has flipped. There's a new combination. So where we had wild type V and W with a mutant, now we have wild type V and W with a Z. So that tells us that Z is in the middle. So the order of our genes is actually V, Z, W. Because if we have V, W plus, and that was on our parent, V, W plus, and we have a double crossover event, that Z is going to move to the other chromosome. So now we know that our gene order is V, Z, W. Next thing we're going to do is determine the distances between the middle two and the flanking genes. So we are going to determine the distance between V and Z and W. Now in this PDF that you have, the original list is all jumbled up. We've got parentals mixed in with single crossovers, and then they give us a second list where they have ordered them in order of frequency. So we've got parental, all those single crossovers, and then the double crossovers. You can leave it in any form that you want to. You will notice that they have left it in the order that is presented, which was VWZ. I personally like to rewrite my chart in the order of our genes. So in the VZW order and in order of least to greatest. I do this because it helps me to visualize, okay, I'm looking for changes between VZ or changes between ZW. You can do it that way if you would prefer. I will probably do it this way in any of my examples that you watch. If you do this, be really careful that you copy things correctly. Take your time and do it slowly. So we've got our parentals, our single crossovers here, and our double crossovers. So let's use this information to determine the distance between the middle and the outside genes. So we've got our chart with our genes written in order. So this means that if we are looking at a chromosome, we've got the V gene, the Z gene in the middle, and the W gene on the outside. So we are now going to look at one of our crossover events and determine which is the single crossover that occurs between V and Z locations. So again, we do this by comparing to the parental combinations. So if we look at this first single crossover event, we find that we have plus W. So let's look at the parents and see which two stay together. Plus Z plus V plus W. So here we have a plus W and a plus W. So they're staying together. Here we have Z and plus staying together. This parent has Z and plus staying together. So that means that the V genes have flipped. So we know that if the V genes have flipped, our single crossover event that occurs are these two in these two sets of offspring. So to determine that the distance between these genes, we are going to count the recombination frequency, count up all the recombinants. So our recombination frequency is going to be the number of recombinants, that's these two right here, plus our double crossover events. So we need our single crossovers for that crossover event, plus all the double crossovers. For recombination frequency, we're going to divide our recombinants by the total. And since it's a frequency, we're going to multiply by 100. So the recombination frequency here is going to be equal to 88 plus 96 plus those double crossover events. Because in a double crossover event, you get a crossover event between VZ and ZW. So we need to account for those events. The total here is 1,000. So our recombination frequency is going to be 188 divided by 1,000 times 100, which means that our recombination frequency is 18.8, which means the Z and the V genes are 18.8 map units apart. So we know that our distance now between our V and Z genes are 18.8 map units. So now let's look at our other event. So we have V, Z, W. We know now that 18.8 map units separate V and Z. Now we need to use our other single crossover information to determine the distance between Z and W. Now, if you've already used this single crossover event, you know that this single crossover event is the one for the other one. But I'm going to walk you through how you would determine if you aren't sure which one is which. I already did it on the other one. All right, so if we look here up on this parent, we have plus Z plus. Over here we have plus Z W. Here we have V plus W, V plus plus. So we see that the flip has occurred here on the W gene. So that means it has occurred somewhere here between Z and W. So if you already figured out one, though, you can just use the other one, the other set. So again, we're going to do the recombination frequency. That's going to be the single crossovers for that gene plus all the double crossovers, divided by your total times 100. So recombination frequency is going to be 61 plus 46 plus 1 plus 3 divided by 1,000 times 100. So recombination frequency is going to be 11.1, which means these genes are located 11.1 map units apart. So these guys are 11.1 map units apart. So the last thing that I would like you to do is make sure that your map makes sense. Remember, these are relative distances. So you'll want to draw out your map. V and Z are farther apart than Z and W. So you want to represent your map in that way. And just draw it. Remember, recombination frequencies produce a relative map, not an absolute map. So, you can just estimate this is about twice as far as the other one. That's good enough. But you don't want to leave it in the middle because we're trying to make a reasonable representation. We're not going to do step 5. Remember that step 5 is calculating for interference. Interference just says that when you have one crossover event between genes, you are less likely to have another crossover event there. So it limits some of the crossing over that can occur.